Today I would like to drive you in a section of my research activity, which is based on the traffic anonymization. So a technique that helps enhancing privacy for the user on the network. This project has led to the development of a novel tool, which is called α-Mon, and this activity has been brought out thanks to the collaboration of the Smart Data at Politecnico Data Center. In order to explain and introduce you to this project, I would like to follow these steps. So I would like, first of all, to introduce you to the concept of traffic monitoring, why we are doing this, what is changing due to the new regulations, which are the common approaches to prevent information disclosure. And then I would like to talk about the α-anonymity and α-Mon, so our novelty that we want to introduce to the world. And finally, I would like to draw some conclusion and possibly have some discussions with you. So what is traffic measurements? Actually, nowadays we try to collect network traffic because they are so important in order to enhance cybersecurity and perform some traffic management. The problem is that by keeping these packets, we are keeping also sensitive information about the users. And so this could be kind of scary. So in the last years, the European government has started to introduce new regulation in order to prevent threatening the user privacy. And so our project sits inside this context. Which are the common approaches? In order to achieve this object, the main activity that has been performed is the anonymization. So it means that we would like to obfuscate sensitive information inside database and so on. There are many algorithms that does this sort of stuff. One of the most important is the key-value anonymity, which means that given a certain database, we want to let them be key anonymous. So let's be at least key entries indistinguishable one another. The problem with these algorithms is that they need to have access to a complete dataset, a scenario in which we cannot sit. In fact, we would like to have an approach which is in a streaming fashion. And so here we would like to introduce the α-anonymity, a new way to anonymize information. As I could introduce before, it sits with strict requirements. First of all, the dataset is not available, as I said before. Then it should work on real time with zero delay and should be so fast in order to be scalable and applicable on a multiple gigabit environment. So what's the real problem here? The real problem is that, as I said before, the algorithms that are used today are based on the access on a complete dataset or batches of it. We would like to do it in a completely streaming fashion with no buffering and zero delay. As shown in this video, I think it is not so fast, but as the car arrives, the tire changes and it goes out. So in the same time the packet should arrive, everything should be anonymized and go out without the waiting for other stuff to come. It's not necessary. Here in this slide, there are some stuff a bit theoretical. I would like to go fast on these and just explain one concept that would be easier to understand in the next slide. So an alpha private quasi-identifier, so a name, something that is subject to the privacy of the user, is a value that is observed at a certain time t, which is associated to less than alpha data subjects in the past delta t time interval. What does it mean? It means that a given information can be considered private if it is related to less than alpha users in the past delta t time that can be defined by the user. This means that, for example, there are many users that are searching for a given name, for example, private.com, and we have set the threshold of alpha equal to 3. Delta t is not so important. It can be any time interval that you prefer. Assuming that first user arrive, we set is delta t, and since we have a counter that sits at 1 here, we are under threshold, and so the information should be private in this sense. The same thing happens if a new user arrives. So here there is a new user, we increment the counter, we are still under threshold, and we set the delta t time interval. In this case, assuming that the 2 users comes again, for example, user 2, we don't increment the interval, the counter, sorry, because we already seen the user in its time interval. So we just need to update it and leave the information private. And the same thing happens if user 1 comes again. We update the delta t time interval, and information is still private. Assuming that now a new user arrives, now this user can let the counter increase, reach the value alpha equal to 3, which was our threshold. The information now can be considered common, so can leak, and we set his time interval. Assuming now that some time has passed, some delta t have expired, like this 2-1, so the counter has been decreased, and just user 3 is active. Assuming that user 2 comes again, its delta t time interval is expired, so it can be considered as a new user. We increment the counter, but since we are still under threshold, the information is considered private, so cannot leak. So this is the base of our algorithm, but our concern is to understand how this algorithm impacts the information that comes inside a given dataset. So we took some traces coming from an operational network, and we tried to apply this algorithm considering the different values of alpha and delta t. From this slide, as we can see, if we try to put the value of alpha equal to 2, we get the 75% of domains obfuscated. What does it mean? It means that the 75% of all the domains inside this dataset have been seen by less or equal to people, which seems quite a lot. But if we try to see this in a different perspective, so in the quantity of traffic that gets anonymization, if we try to still keep alpha equal to 2, the quantity of traffic that gets obfuscation is about the 10%. So most of the information that would be useful for further analysis are still kept inside the packets that we could keep thanks to this data collection. What's the lesson that we learned from here? The lesson is that the popular domain carry little sensitive information about the user, but they are responsible for the majority of the traffic inside the network. So, for example, if we get names like Google and Facebook, anyone goes to these kind of websites, so there are no concerns on the privacy of the different users. So letting this information by doesn't challenge any concern of privacy. So now this is the theoretical stuff. We took everything from there and we put it inside a practical tool and that can be used inside a given network. There are many requirements, as you could imagine, which are flexibility, first of all. It should support, obviously, the alpha-anonymity because it is based on this concept. It should support the anonymization on all the protocol layer, should be scalable and deployable on high-speed links, and should support multiple legacy applications with different anonymization requirements. This seems quite confusing, maybe, but it would be easier to see this picture that can explain better the what is happening actually. Assuming that we have some networks with a splitter that gives the packets to a replier. The replier has just the ability of copying the packets to all the different consumers. But if we try, for example, substituting the replier with α-Mon, we can get many functionality. For example, first of all, we can have an unbounded number of input ports, so we can link many networks to the same device. But we can have also many output, an unbounded number of output, but each output can be configured differently according to the need of the machine that is at the bottom of this picture. Assuming, for example, that the security monitor needs a very low level of anonymization because maybe it's useful to see what is happening. A network monitoring maybe need a high level of anonymization because we would like to delete all the sensitive information because are not useful for the purpose of the network monitoring, and so on. So this is the concept of α-Mon and how it sits inside a given network. This tool has been implemented in a modular way because we would like to make it easy to be expanded. So we have a core system on which can be attached many blocks, which are easy to be put inside because just you need to write the code in order to manage a given protocol or a given layer and add it inside the central module of this system. Nowadays, this product is covering all the ISO protocol layer from layer 2 to layer 7, anonymized everything from the MAC address and IP address to the application level. Now I would like to show you why this tool is so powerful and how it performs in a real environment. So we took some traces from an operational network, and we have the ISP full, which represents a typical workload, ISP header, which is the same trace as before basically, but we deprived all the packets of their payload, so we're trying to benchmark the packet capture. And finally, we have the DNS packet trace, which is based on just DNS traffic that has the aim on benchmarking the alpha-anonymity module. The testbed is quite easy and straightforward, so we have a traffic generator that keeps these traces and tries to send all the packets as fast as possible to the α-Mon machine that then sends to consumers the anonymized copy of a given packet. We try to give to α-Mon the highest speed as possible without having any sort of losses in the middle. At the end, we tried also to increase the number of consumers in order to see how the system performs by adding more computational concerns. Assuming that we have the simplest system of them all, so a generator and one consumer, with the use of just one core, thanks to our limitation of hardware, we could obtain just 10 gigabit per second anonymization. Obviously, this value drops if we try to increase the number of consumers at the end. For example, with the 2 consumers, it drops, but it needs just 3 calls in order to get the 10 gigabit benchmark. The same thing happens if we put 4 consumers. Obviously, in this case, we need 6 calls in order to achieve the 10 gigabits per second. But what we can see from this picture, and this is really interesting, is that the increase on power is linear to the increasing of the number of cores. So basically, by just adding more cores, we can achieve higher speed given the situation in which we fall. Then we get the ISP header. Obviously, here we have a drop in performance because since the packets are smaller, the number of packets that are analyzed in the unit of time is greater. So obviously, in this case, we need 5 cores to achieve the same performance as before. The same situation happens if we try to add more consumers at the end, but as we can see, the performance scales linearly with the addition of new calls. So probably by adding other calls, we could reach the 10 gigabit benchmark. A drop is also present in terms of the DNS, because obviously each packet should go through all the anonymization steps, which are really heavy. But obviously, in this situation, with just one call, we can hit the 0.66 gigabits per second, which is quite a remarkable result, by obtaining 3 gigabits per second with pure DNS traffic with 8 core, which is a quite remarkable achievement given what the system has to do. The drop obviously is present by adding new consumers, but the linear increase in performance is still there. So by adding calls, we are confident that we can reach higher speed and reach maybe the 10 gigabit benchmark that we saw at the beginning of this test session. So here I would like to draw some conclusions by wrapping up everything that I've presented to you. So α-Mon is a flexible and modular tool that can apply anonymization with a rich set of policies. It can provide anonymization to legacy monitors that need different traffic visibility. It is based on a streaming anonymization technique. It is scalable and efficient, and we had the possibility to test on a real environment this tool, since it is today active inside the Politecnico network. And today, actually, we are analyzing all the information that comes from α-Mon. So we are really happy that in this way, we are obtaining information about the traffic without trading the privacy of the user that serve the Politecnico network. So I would like to thank you for your attention, and I would be really happy to answer any question. Thank you.